first to get you energized, of course, the show of hands. So, who has kids? Almost. Who knows kids in his neighborhood? Maybe his neighbors or his brother, sister. Okay. Who used to be a kid? Okay, so I have everybody now. Okay. So if you were a kid, or you know a kid, you have a kid, you probably know this toy. Yeah, so this is a learning toy. What kind of learning toy? It's a toy with which you can learn how to rank. You can rank the sizes of the rings in the right order. And this is something you can teach your kids, and they love it. Only at the first try, they end up something like this. This is a good try. It's a nice try because all the rings are on there and the ball is on top. So this is already quite difficult, but it's not exactly what we want. So what we do is we show them the example again, and we try to learn it, and then your kid tries to rank it again, and it turns out like this. The question is this right or is it wrong? I would say it's perfect. I mean, it's nicely ordered in a certain way. It's not the exact same thing as the example, but it's good. So today we're also going to talk about learning and ranking. Only we use a different toy. We use Elasticsearch, and we're going to combine it with machine learning. I'm Jettro Coenradie. I'm a fellow at Luminis Amsterdam. I'm specialized in Elasticsearch, and I love experimenting with machine learning. And if you want to follow me on Twitter or whatever, then all the things are here.
Yes, my name is Byron Voorbach. I'm a search and data engineer at Luminis Amsterdam. And my daily work day, I'm mostly busy with building and optimizing search engines. Mostly Elasticsearch.
Yeah. So I shouldn't do the Beauty and the Beast joke, do it? No, I shouldn't do it. No, okay, so don't do it. Okay, let's talk about e-commerce and ranking and search. So when I was preparing for this talk, I do talks on a regular basis. It's not always the same subject, but I do some talks these years. I wanted to treat myself, so I wanted to buy something. So I had a thing that you could move the slides with, but it was a bit old and rusty. And I saw this TED talk, and someone had something there that you could do. You could point, and you had this. I thought, wow, this is cool. I want that as well. So what I did, I went to internet, of course, and I started looking at the WCAM, because I knew you can buy more stuff at the WCAM than close. And I found it. It was here, the 5th result. But yeah, I'm Dutch, so you want to see if it's cheaper, maybe somewhere else. So I tried Coolblue. I did the same thing, the same search, and yeah, there it is again. It's slightly more expensive, but let's try another one. So I went to the website of bol.com, and it's not there. So I happen to know someone who works for bol.com or at bol.com, and he knows a lot about search. And I'm asking him now if he can maybe explain why this cool device is not on the screen.
Yes. So for the last 2 years, I've been helping out bol.com with their transition to Elasticsearch. So I know a little bit what's going on here. One of the major differences between bol.com and WCAM and Coolblue is that, I don't know if it's really visible for people in the back, but you can see that there are 237 results for the word presenter, which is a lot more than we saw on the other 2 websites. So bol.com has a lot more data. Now, another thing you notice is we just search for presenter, which is a pretty common and pretty broad term, meaning that we can get any presenter that is out there. So if we dive a little bit closer into this example, let's change our search to Logitech presenter, and we can actually see that the product actually exists at bol.com, so they're also selling it. But if you look on the top, you can see a drop-down in which you can sort the products from the results from your search. And by default, it says we sort on relevance. Well, what is relevance? For Jettro, a more expensive, fancy presenter is more relevant, but for me, I would just go with a cheap one because, yeah, although the feature is cool, it's a lot of money. So what we're gonna So the relevance part is pretty important because the first thing that people see when they see the search result is the first hit or the second hit. And it actually has been shown in studies that the click-through rate for positions is higher in the top 3 results. So you want to make sure that if you sort on relevance, that you have the most relevant products on top for either that user or for your business. So since Bol.com is not like software we have running on our computer, but we want to show you today how we can improve the search or improve the relevance by using machine learning, we made a small demo. We have a search engine here, which contains the top 500 albums from the Rolling Stones. Not the Rolling Stones itself, but by the magazine Rolling Stone.
Top 500.
Yes, exactly. So, and Jettro can show that we can search on that.
Yeah, so let's do a few of the queries. First one, for instance, U2. You can see that the results are quite okay. The first 5 albums are from U2, and then there's Radiohead, the Beatles. And well, of course, we can look for something else as well. Let's get a little bit more guitars. Let's search for Metallica. There's 2 albums from Metallica in the top 500, but there's also the Beatles. Okay, why is there the Beatles? So we click on it, and maybe we can... okay, so for some reason Metallica is in the information box of the Beatles as well, so this album will be in the result list for the Beatles. Well, let's do one more. Let's check Rolling, which I don't really like to type out Rolling Stones completely, but if I type Rolling, from the Rolling Stones, I see the first album is from the Rolling Stones, but the second album is Howling Wolf, the third, well, Professor Longhair, Dr. John. Okay, this is not what I was looking for. So let's see if we can improve this.
Yep. So just to get back on the demo, how do we get from our search term U2 in the first examples to a list of albums? Like, how did we build this? Well, meet Elasticsearch. Can I see a show of hands on how many people here know Elasticsearch? Ooh. That's a lot.
Maybe we can go faster.
Yeah, we can go. Then we can go a bit faster on the next slides because I prepared a little intro into Elasticsearch. Elasticsearch is a distributed search engine. We have been using it since the beginning. We love it. We use it for a lot of projects. We help commit on it. So we do a lot with it. But actually, how Elasticsearch works is you have Elasticsearch standing there. You have an index, and what you're going to do is you're going to feed data into it. Documents, and in our case right now, it's the data from the Rolling 500. So we store the documents into Elasticsearch, and at that point, the documents will go through an analysis phase. During this analysis phase, tokens will be extracted from the documents so that if we search for U2, we actually get documents that have U2 somewhere in the text. The analyzed data gets stored into an inverted index, and I'll show how that looks like and how that works in a second, which most of the people here already know. And the next step would be I have a query which we can send to Elastic, which will match the documents in our inverted index, and the result will be returned. So what that looks like if we start adding our data from the Rolling 500, let's say we have some documents that just contain an artist field. So we have, for instance, we insert a document for U2 with doc ID number 1. It gets put into the inverted index. We get the term U2, we have a doc ID, and we have a total term frequency. So how often this term occurs in the complete corpus of your index. So if we move further and we start adding more data, you can see that the input text gets split on white space and gets put into the inverted index. That's how we found Rolling, and how we will find Rolling Stones if you type both of them. Now let's add one more, Rage Against the Machine. And the last one is when you have another document that contains a term which already exists, then it will be increased, so the extra doc ID will get added, and the TTF will be increased by 1. So this is in short how Elasticsearch, or actually Lucene, internals work. Just to quickly go over what documents and queries look like for Elasticsearch, this is an example of a document. You can see that we have an album name, we have some information, we have a label, we have an artist, and these fields are fields that we can search on, which we'll also be using later to improve our relevance. This is an example of a query. We have an index called Rolling 500, which we're querying against through the JSON curl API. And we have a query where we search for U2, and we search on the 3 fields which we just indexed. So artist, information, and album. So what happens underwater is as soon as you send a query to Elasticsearch, it will run against the inverted index, and it will try and match the tokens from your query against the tokens inside the inverted index. And from that matching, documents are returned, and let's say these numbers are document IDs. So by matching these document IDs are returned, then the next step will be is to score those documents, which will be done by a ranking algorithm internal into Elastic. This is the default ranking algorithm in Elastic. And this might look a bit scary at first, but it's actually the TF versus the IDF with some normalization factors. And the takeaway from this is that the IDF score is based on how often a term occurs inside the whole corpus. So if your search term occurs more in other documents, then your document will be less scored. Then for the term frequency, sorry, let's just click through this. So the amount of docs, how more often it occurs, the lower the score is. Then for the term frequency means that if the term occurs more often inside a document, then the score will be higher. So just a small takeaway that if you incorporate the field length into that the longer a field is, the less important a certain document is. So if you search for U2 and you have a hit in the title, which is a really short field, then it means that the document is probably more interesting than, for instance, the Metallica we saw, which had a match in the information. So next to having BM25 by default, it can give a pretty good score if you just use the basics of Elastic. But there is a way of modifying that, the relevance yourself. So you can add certain boost parameters, or you can add some functions to improve the score. So on the left, you can see that we do a query where we search for U2, but if the document matched in the artist field, then we say it's twice as important than it would match in the information field. So we already have some knowledge up front, knowing which fields are more important than the others. Then you can use field-centric boosting. A second example is a function score where we say we have some information about this document, inside a variable inside this document which says how important it is. So we can store the amount of likes with a certain document, so that we can later say, okay, we want to boost on the actual value inside that document. It could also be price, likes, favorites, whatever. And then there's a third one, and that's the decay function. So for instance, we search for U2 and we say that every album that has been released in the first year from now is more relevant than the older ones. Well, for the rolling 500 case, it's not really a good decay because all the albums are super old.
You didn't know most of them. So.
No, that's true. It's all for my time. So these are like just 3 ways of changing the boost and changing the relevance.
That's me.
Which brings to the next way of doing things.
Yeah, so like Byron mentioned, you can influence the boosting yourself, but then you have to decide on the boosting factors yourself as well, which is not always easy. I mean, I've visited customers where there was in the code a factor of 2,376, and I asked them, what's this boosting factor? Yeah, we don't know. It just seemed to work. That was actually the answer. And the problem then is that the next person that comes by, he says, well, I'm having this query, but I would like to have this result. So I need to change this boost factor a bit, and then this query works better, but now the other one doesn't work anymore. So you could do this by hand with a lot of testing. But what you could also do is you could use learning to rank, which is a way to use machine learning using data to find the most optimal, what you could call boosting factors. It's just, it works a little bit different, which I hope that will be clear at the end of the presentation. So on this slide, there's also a definition from learning to rank. I think every serious presentation these days includes a link to Wikipedia. So I have it, check. So this is a serious presentation. Yeah. So let's continue. We're going to talk now a little bit about machine learning, and actually we're going to talk about supervised machine learning. If you want to know what unsupervised machine learning is, then come to me after the talk, because we're not going to talk about this. What supervised machine learning means is that we have a data set which has an input and a known output. And then we can use this input and output to train a model. Let's give an example with the housing market. So imagine you want to estimate the selling price of a house based on the square footage and the amount of rooms. So I have an immense number of test data, 3, and with this data, I know that my input is the number of rooms, the amount of square footage, and I know that it was sold for this amount. So now we're going to choose a model, use this training data to configure the model, and then with the model, we're going to predict for these same houses the price. Well, one could argue if this is a good prediction or not. So there is an error between the actual labeled output and the predicted output. Well, this is what machine learning is about. So now, in the next step, we're going to tune the parameters of the model a little bit and do a prediction again, see if the error becomes smaller, and then with the smallest error, we know that we might have a good model to do the prediction. Well, that's nice for houses. But as you saw in the example, we're not selling houses. We're having a search engine. Well, it could be a search engine for an e-commerce website, but it's different. What we're not looking at the right price. Well, that could be an interesting example though, but that's not what we're going to talk about. What we are talking about is having the right order of the documents that you return. So it's a slightly different problem. If we go into the search area, we have, in this case, 4 inputs, being 4 queries. And for each query, we know the order of the documents that we want to return. So we have, again, input, and we know the output. So we can do the same thing. We can come up with a model, train the parameters, and do a prediction. Now that we have the prediction, we need some way to compare the predicted output with the actual output to train our model. So there will be an error between these two. We're going to talk about what the error looks like, but again, using this error, we throw it back into the model and then try to tune the parameters better, do a new prediction, and see if it improves. So there's a few ways to evaluate the errors, to do the model evaluation, the errors. One is binary relevance. With binary relevance, we look at a document and we say, this document that you returned is relevant or not. Well, there's 2 methods that we could do, the mean average precision, which we will have a look at, and there's precision and there's lots of others as well. Another way is to use a graded relevance. So now we have, it's slightly more relevant. So we could say from 0 to 4. If it's a 4, it's really relevant. If it's a 0, it's not relevant at all. And in between, there is a scale of relevance, a grade. This is used by the... We practiced this like 2 times, and I keep forgetting the D. Discounted, thank you, Byron. Discounted cumulative gain. And the second one is the normalized discounted cumulative gain. And this only takes the relevance. Then there is a second graded relevance, which is called the cascade-based. And this also takes into consideration if you click the 3rd item, then most likely the 2 items before that were not relevant to you. At least that's what we think, because you click the 3rd item. And that's what the error does. Well, to give you a slightly better understanding of what we mean, because this concept is really important, let's check with an example. So we have the query U2. We return 5 documents. Anyone colorblind here? Yeah, oh yeah, I knew that one. Yeah. So I'm going to explain it to you. So there's 2 colors, green and orange. The top, the 3rd and the 5th one are green, and the 2nd and the 4th one is orange. No, but now you know, okay? So keep it in mind. For the others, I just will call it green and orange. So when we calculate the average precision, we take the ones that are relevant, so being the first one is relevant, and out of 1, that one is relevant, so we call it 1. Then the second one is not relevant, so we skip it for now. The 3rd one is relevant, but now we have from the first 3 items, we have 2 relevant items. Well, that's 0, 6.7. Do it again for the 4th and the 5th. The 5th one, now 3 out of 5 is relevant. So we have 3 average precisions for 1, 3, and 5. And then we take the mean average precision, which takes the mean of these 3. So this is what's called the map of 5, map at 5. This is one way. This is binary relevance, relevant or not. So if we would go to the discounted cumulative gain, then there you see that we have an estimated output, but there is a rel thing in there as well. The colors are all the same, by the way. Rel is 3, means that the actual document in the output that we know, that it has a relevance of 3. But the order could be different, but the output is taken, the relevance is taken from the output itself. And then we calculate the discounted cumulative gain, and what it does, it takes the position where the document is into consideration, and we expect, just like with the click-through rate that Byron showed, that the lower the document is in the list, the less important we think it is. So if the document is on top and it is right, it's the most relevant one, then we give it extra, and if it's down the list, then we give it less numbers. So if you would do this all the way with all the 5 steps, you would see that in the end we have a DCG value of 807. But if we would take 10 items, then it would always increase. If we take 15 items, it would increase because it's added, it's cumulative. So that's where the normalized DCG comes in place. And there we first calculate the max DCG with the actual values. So the second column with the Y is what we know. This would have been the ideal output. And then we calculate the DCG, and we also calculate the DCG for the predicted output. And then we can calculate per line what the normalized distributed, it's with the D, distributed, NDCG value is. I hope that this makes it a little bit clearer than just the description. So a little bit of recap. We have input and output, X and Y. We put it into the model. We have chosen an algorithm. And now we're going to tune the parameters. We're going to do a prediction. Then when we've done the prediction, we use a cost function. And the cost function checks the predicted output with the output that we know. And it will tune the parameters, and we try again until we find the most optimal value for the cost function. So for the model, there's a few different approaches. There is first the pointwise approach, where we would look at each document separate. We would calculate a score, indicating how relevant that document is, and then we just sort based on the score. This is what the default Elasticsearch way is, and what a lot of other search engines do as well. So this would be the outcome of the order, because the score is now sorted from top to bottom. The pairwise approach is a bit different. There we go through all the documents, we make pairs, and we don't really calculate the score. The only thing that we say, this one is more relevant than that one. And that's the way how we sort them. So we have 2, and then this one's more important. So in this case, the 23 document is more important than the 88. Then we would do that for the next pair. We would compare 88 to 45. And in this case, we say 45 is more important than 88. Well, we still have to do another comparison, because we have to compare 23 with 45. And we say that 23 is more important. We get the same result back. Now there is a final one, and the listwise approach. And the listwise approach does it all at the same time. It just takes the list and somehow determines the right order. Yeah, somehow. I didn't know how to put it into a picture, because it's quite complicated. It's also the newest ones, and this is what a lot of smart people at universities are looking at the moment. Usually I stick to the pairwise. But believe me, they do come with the right sort order. But you can try it yourself. So how can you try yourself? Well, we do have a few steps with learning to rank. First, you have to create a judgment list. This is what would be the actual values that you would expect, so the ground truth. Then you have to define the features for the model that we are going to train on. You have to log the features during usage. If that's not clear, stay with us. It will become clear. We have to train and test the model. Then we have to deploy the model to production, and there is a feedback loop that we can do even more with. So the judgment list, well, I already mentioned, it's about labeled data. There's 2 ways to get this judgment list. One is an expert panel. The problem is that it's very time consuming. Well, luckily for the Rolling Stone 500, you have the expert panel on the floor. I mean, we are by far the experts on this list. So we really knew how to create this judgment list. The problem is it's error prone. because there is a matter of opinion in there as well. And you have to have a little bit of context. So to see if you believe me, we're going to do an experiment. Yeah, sorry, I have to ask you to raise up hands more often, but this is the final one. We're going to do the pet or not experiment. So you tell me if you see a pet on the picture. If you see a pet, raise your hand. I think we're clear. I think everybody knows this is a pet. Okay, and now. I knew it, Ralph. I knew it would be you who would raise his hand. Okay, so I think we agreed there's no pet on this picture. I mean, he's kind, he's nice, but it's not a pet. And now, who thinks it's a pet? I see a few. So, if you think this is a pet and you would be in the expert panel, then there would be pet as a label. But if it was someone next to you who didn't raise his hand, it could have been that it's not a pet. So that's what makes it hard with an expert panel. It's opinionated, so you have to give a little bit of guidelines, and yeah, there is a risk. Yeah, so another way, using an expert panel has its advantages, but also disadvantages, so we can also use implicit feedback. And implicit feedback has to do with logging user behavior, for instance. We compare the actual clicks to the predicted clicks, so if we think that 20% of the people that come into our search engine would click the first item and we see that it's actually just 10%, then most likely that item was not relevant. Because we would expect 20% and it was 10%. So it's most likely not relevant. Another thing that you should also take into consideration when using clicks for judgment list is that a click might not be a judgment. If we look at this example, where someone would search for Adobe, the expert panel would most likely put the Adobe homepage on the top and would say this is the most relevant item. But if you would see the click statistics, it could well be that this one, the PDF reader, would be clicked a lot more. Does it make it immediately a lot more relevant than the other one? I don't know. It could be because a lot of people click it. But like 2, 3, well, maybe 5 years ago, most likely there would be Flash Player in here. But yeah, these days that's not relevant anymore. So when you have these implicit feedback, you can do two things with it. You can use it as a feature, which Byron is going to show us in a while. And you can also use it to create this ground truth. So really create this list so that you don't need an expert panel anymore. And we're going to show that at the end as well.
All right, so now we have some background information on Elastic and learning to rank. Now let's do the fun stuff. Let's try and improve our search by incorporating learning to rank. So the guys over at Open Source Connections built a plugin for Elasticsearch called Elasticsearch Learning to Rank, which allows us to define a model, train it, and use it to rescore our documents. So let's take a look at our judgment list. This is the format of a Python library that we use and which it needs to parse in order to train our model. So let's quickly go over it. It might look a little bit like a mess at first, but it's actually sort of like a table structure. So on top, you can see grade, query ID, doc ID, and title, which are the columns that the data needs to be aligned in. So as you can see on the left, we have a set of grades. 4 meaning super relevant, 0 meaning not relevant at all. Then next to that, we have a QID, query ID. If you look on the top, you can see that QID1 stands for U2, QID2 stands for Metallica, and QID3 for the Beatles. If we take the example of Metallica, which we saw before, we had 2 hits and we had a 3rd hit for the Beatles, which is also being reflected here. Because you can see on the left side where we have a score of 0, we have a QID of 2 for Metallica, and we can see that that was the Beatles hit. So the next row is the document IDs, which you need to add because you need to know which documents were returned for the certain query, what its relevance was. And we have a title next to it. So this is our ground truth. This is what we say. This is the actual order things need to be in. Let's go to next. So now that we created our ground truth, we need to define features. And for features, we need to say what is actually important about these documents. For using features, you can use raw term statistics, for which the guys in the plugin allow to get those information out. So you can get the raw term statistics, the document frequency, the total term frequency, and you can combine those with min and max. So you can say, I want the max frequency of a certain term as a feature. And all these features are defined as Elasticsearch queries. So what that looks like is like this. We define a feature on our artist field, because when a match occurs in artist, then that's probably important, so we want to train on that. So what we'll be doing for our example is we'll be creating four features that we're going to train our model on. First one is artist, and we have two more on information and on album. So we have 3 text fields that we want to train on. The fourth one is we try to incorporate clicks into our example. So as you do a search for U2, you click on one of the albums. A click is stored with the document, so we know how often it has been clicked. So we can add a function score, as I explained earlier, and we want to use that as a feature for training our model. Next step would be logging the features. So we have our 4 features, and now we're going to use our data, our judgment list, to run through our model to actually log the features, so log the actual values. Now, what we can see is we have a 1 with a colon and then the score. The first feature that we added was on artist. And as we can see, some of the values have 0, meaning that for that query, that Elasticsearch query, there was actually no hit, so the score is 0. The other ones have a little bit higher score, and that's actually the raw BM25 score of the ranking algorithm I explained before. So we can see the scores for each of the features, and we will put this in the model, and later we will use this for actually training and testing the model. So the plugin Underwater uses Ranklib, which is a Java library which contains 10 different models that you can use. You can specify separate train, validation, and test sets. And what that means is that you have a set of data which you know you're going to be testing with. You take roughly about 60% of the data for actually training your test set. Then you use 20% for testing the actual model. And as soon as you did your testing and you think you have the right parameters, you use the last 20% to actually validate that your model was not purely optimized for your test set. And if you have some features in your, or you have some data which is not normalized, but you would like to have it use it normalized, then the plugin can normalize the data for you before using it for your model. So if you want to know which kind of models are supported in the Ranklib, then now would be a good time to take a screenshot, because I'm not going to go over all of them. First off, because it's too much, and second, because we haven't used all of them yet. So we don't know exactly for which use case which model would best apply. But the takeaway from this is that there's a lot of different models, and for your use case, a specific model might work best. Then in the plugin, there are a few evaluation metrics. 3 of them Jettro already talked about, and there are 3 others that you can also use. So what we did is we have our judgment list, we logged our features, so we made an overview, like a matrix, for seeing for which model with which evaluation metrics gives out which score. And we take out 2 of these because 2 of them, one of them actually really stands out, and that's rank boost. You can see that these scores that you see, except for the DCG, are all normalized, meaning that a score of 1 means you have a perfect list. So your test set actually was perfect according to what comes out of the model. Now, for a rank boost, you can see that the scores are 1. So this could mean that either it's really good, or it's just 1 because of overfitting. Another one that is actually has some pretty good scores is Lambda Mart. And that's the one we chose for our demo, which Jettro will show in a bit what that will look like and what it will do to our search results. So next step, we trained the model, we validated it, we had some error cost function tuning our parameters, and now we can deploy the model. So the model is where we can upload the model to Elasticsearch, and from that point we can use that to rescore documents based on our model. So this is what that looks like in an Elasticsearch query. So we still have our query, we search for album, we search for artist, we search in information, but what we have now extra is we have a rescore in our query. And what this actually says is we want to rescore the top 20 results based on our model test number 6. So what that will look like, we're going to see now. So we extended our search with not just having basic search, but we can actually compare our model versus our original scoring.
Yeah.
Let's search for something.
Okay, we're going to search for something. Well, let's first check the rank boost one, which had the factor of 1, and look for something like the U2 that we tried before. Well, this result was already okay, and luckily it stays okay. So the model doesn't make it worse. That's good to know as well. Now let's try another one. Let's see if we could do something that I know we didn't really train on. The rolling was not in our judgment list. And now let's see what happens. So on the left side is the one without machine learning, without the learning to rank. And on the right one, we did apply learning to rank, in this case, the rank boost model. And we see that it doesn't really improve. So most likely there was a problem with overfitting in the rank boost case, which is not that weird if you would see the judgment list that we created, because I think it has like 5 queries. So it's not that strange. But now let's try it with LambdaMart. With LambdaMart, the results become a lot better. So as you can see on the right side now, we see that the Rolling Stones are mentioned for all the top items. So I guess in this scenario, it worked.
Pretty good.
Yeah, pretty good. So we could say, let's try one other. Let's try the Beatles, for instance. And the Beatles is also quite okay. Any other artists you want to look for? It's a Rolling Stone Top 500, so there's not a lot in there. Okay, let's move on to the presentation. Okay, so I promised you a point 6, which is called the feedback loop. And it's called feedback loop because we use the feedback that is made by the users. So we are going to use clicks, and we use these clicks to come up with a judgment list. That's the goal. So we don't have to have an expert panel anymore. We can do it using you guys just searching and clicking and interacting and giving us feedback. So there, for the click models, you can do a few things. You could use the random click model. In this case, we don't care where in the list the item is. The item that's clicked most is most likely the most relevant item. That's what the random click model does. Then we have the click-through rate model. And this one is more like I discussed a few minutes ago, that if you click on the first one, but your first one has 10% of the clicks, while we would expect 20% of the clicks, it's most likely less relevant. And if you click on the fifth one, which should have around 5%, and it turns out it's around 10 to 15%, that is most likely more relevant. And that's what we use in the model as well. And then there is the cascade model. In the cascade model, we assume people make only one click during their search session. So they do a query and they click on one item. If it's the fourth item, then that item is the relevant item, indicating that the other three that were before are not relevant. But this is a bit weird if you think about how people interact with a search engine. They often click on an item, see if it's relevant or not. If it's not relevant, they go back, click on the next item, and that's not possible with a cascade model. But with the dynamic Bayesian network model, this is what is possible. So with this model, we can record multiple clicks, and if a user clicks on the second item, comes back, clicks on the third item, comes back, clicks on the fourth item, moves away, then the fourth item most likely was the one he was looking for. Or he just gave up. Yeah, that's hard. So let's assume that everybody finds what he's looking for, and if he leaves, he was satisfied. That's what the dynamic Bayesian network is about. So in this diagram, that it shows a little bit what I discussed. So you have the top one with the E's. The E says a user did examine a URL. Then if he examined the URL, and which could contain a snippet and maybe a picture, and he finds it attractive, then he would click on the item. Then he goes to sort of a landing page of that product. Then he checks it out. If he was satisfied, he will leave. If he's not satisfied, he will come back. And then he will take this arrow on the right side. And he will take the next item to examine. And then we move on and we continue. Then at the bottom, there are two parameters, the AU and the SU. These are parameters to tune the model. So these are the ones that we're going to optimize if we start training the model and then start doing predictions with it. If you want to learn more about the dynamic Bayesian network model, there is a link on the right side that you can use with an article explaining it a little bit more extensive. So let's discuss our setup. On the left, we have the screen. This is our application. So here we record the clicks of users. These are written to logs, and these logs are parsed using logstash and sent into Elasticsearch. Then we have an application, the rolling 500, and it takes these click logs and it creates sort of a structure that is required by var epsilon, another Python library that we use. And this var epsilon library takes this learning data in this specific structure and it creates our judgment list. Well, almost. It creates something that we can use to create our judgment list. Then when we have these judgments, we will send it to our plugin, the Learning to Rank plugin, which updates the models, sends it back to Elasticsearch, and we can start all over again. That's what we're going to do. So this is part of the logs. This is in the format that var epsilon requires. Let's zoom in on one line. This is one query that someone searched for Madonna. And just to give it a better view, it's the same thing. The first item was the query ID. The second item was the text that was actually queried on. Then we have some things that we don't use, but you could use them if you want to make it more advanced. Then there is the document IDs, which are the IDs that were actually returned when executing that query, and also in the order that they were returned. And the final row, there's the false, false, false again that we don't use. That's why it's false. And then there is clicks, which registers the clicks that the user did. So in this case, which item was the most relevant item according to dynamic Bayesian network? The third item. Yeah, thank you. So this is what it looks like. var epsilon generates this list in the second column. So there's this list. I can use it once more, just because it's cool. And then we have another Python script, and this Python script then parses it into our judgment list structure. And this is something that you should recognize by now. This has all the queries that we've done. This is what Byron has shown us, and this is the judgment. So it's the same thing that we did before. Okay, so we do a demo again. And this time, we're going to use this file that we created, and we're going to put it into our system, into Elasticsearch. So we run this Python thing. You see, I'm a Java programmer. That's why I call everything this Python thing, because I actually don't really understand it a lot. But I'm learning about machine learning, so I also have to learn about Python, because a lot is done in Python. If you look closely, you see there's something called finished, and then there's an NDCG value. These are all the different models that have been trained. And then it results into an NDCG. Well, it's not really important to show. Just believe me that it's there. And then we go back. So now underneath, we change the models in Elasticsearch, and we're going to do the query again. Oh, this didn't really help, did it? So the result became crap. I think in this case, we could say that for the Beatles, the model didn't work very well. And I think, again, for rolling, the model also doesn't really work very well. So what happened? Well, I told you in the beginning that you have the best expert panel on the floor. So of course we are a lot better than the machine learning algorithm. And we can do a much better judgment list than the machine learning algorithm can do. Or maybe we choose the wrong model, or we don't have enough data. And if you look at the sample that we created, you could also see that there's, if you look for U2, then you could click all the U2 albums. But maybe I'm curious to see why, if I search for U2, Radiohead would be there as well. So I click Radiohead, or just what I did in the sample with Metallica. I clicked on the Beatles, and then I searched in the Beatles why it was returned for Metallica. Well, if you think back at what happens, I would get back this array of, for Metallica, 3 items, and the 3rd item was clicked. Because I was curious why Metallica was in, the Beatles was in the list for Metallica. So actually, I messed up. So don't blame machine learning, don't blame the model. I just took the wrong model for the problem at hand. And I think that's very important when you start experimenting in this world, that what could work for someone doesn't always have to work for you as well. You have to think close about what is your intention, and you have to experiment. So try different models, see what you get out of it, check the scores, check the evaluation metrics that we discussed. Also, play around with the evaluation metrics. It could well be that a different evaluation metric works better for you with another model. And yeah, I think in the end, the goal is to have fun while doing this. And if you're in the business world, then prepare to spend time on it. If it's more than a playground, then don't feel that you could fix this in a week. This is something that you have to keep doing because things change. And you have to look very closely at what happens, the data that you collect. Do I really collect the right data? Is my data clean? There's a lot of steps that you can take. That's it. So we are on time. So we have time for questions if you want to. Let's go to the middle first.
Imagine you have a very big index and you have certain domains that reflect the data. So to say, the index has data from car manufacturer or from like index data about animals, for example. Is it also a good idea to let the user have the choice to pick a model which works the best for him?
Do you think a user would do that? If you think about the context in the beginning that we're going for a bol.com or another e-commerce website, I think what they did is to provide a sorting algorithm, at least for that you could change the sorting. But I don't know. Do you know statistics about how many times it's used?
No. But I do know that what you're saying is actually going more into the way of personalized search. So what you could do is you could record searches and clicks for a specific user and train a specific model for that user. So that's something you could do, which depends on how large your business is that you actually want to do that, because it can be very costly to do. But I don't know if you would let your users themselves choose a model for sorting.
But it's a good discussion if you have like the bol.com website, which has a lot of different categories, that they could train the results for one category different than for another category, for instance. That is something that is being done. Yeah. Okay, other questions?
I have a pretty similar question. So first of all, I really like the presentation. Very
Thank you.
But can you also train, maybe kind of similar, can you also train a model for personalized search? So for example, when I search for something, if I'm segmented, that I, for example, I like, in the example of bol.com, I like expensive items. And somehow the items that are expensive get ranked more according to my search compared to somebody else who likes cheap items.
Yeah, so I think you could do that with machine learning, but there is already an easier way of doing that by just using boost values. So if you know that a certain user is searching something, you could fetch their information to see what they think is important, and you could add boost factors for that. So that's the easiest way of doing it. Yes, I think you could use a model or machine learning for that. The only downside is that we've seen that you need a lot of data before actually things get more relevant. And we just started with this application, and then we noticed that we really need a lot of data, and I don't know how much you would actually need for things to become more relevant for a user. So I don't know if machine learning in that sense is the best fit for that, but you can already do that by default in Elastic.
It would not be smart to start out with this. I mean, I would always start with a simpler approach, and only if you're not satisfied with the results, jump into this track, because it's a lot more work.
In case of training, you told that it was a wise idea to record the logs in a session. Is there any sweet spot in how large such a session should be?
So, not really clear on the session.
Yeah, well, in case of e-commerce, you can say a session is when a user logged on, and then after a period of no communication, the session ends. But in case of bol.com, a session could be I'm searching in handtassen, or I'm searching in computer stuff. When does a session end?
Yeah, well, so when does the session end is a good question, of course, and it's I could say the consultancy answer. It depends. To my opinion, the session for us, the session ends the moment you start a new query. Mm-hmm. So the moment you change the query, then you start a new session. But that is in the models that we have been using so far. I know there is a lot of experimentation being done to collect everything and to see if people refine their query. So I think the presenter case is a good example. So if I was searching for presenter, then Byron showed us that you would get a lot better results when you add Logitech to it. And in the current examples, that would be a new query. So it would get a new query ID with a different flow. But so that's the way we have been using it so far. Yeah.
But there's also a lot of different ways you can do with that. Like if somebody just minimally changes their search term to something similar, you could use that information also in your feedback loop to, for instance, automatically train synonyms or do spelling correction. Because you know that users have been changing their query to refine where they actually want to go. And as soon as they buy a product after doing 3 different searches, you might be able to link all of those searches together and improve the next time someone searches for that term.
So create a contextual scope.
Yeah, but it's hard to narrow that down to like how it could be, because if someone uses a synonym for a search term, would you say that's still the same search term? Yeah.
Searching is easy, that's fine.
Yes.
Other questions? Yes.
How much data do you need for training?
Yes. How much data do you need? I really don't know. I think it depends a lot on the amount of features that you want to introduce. It depends on the amount of records that you have. So if you have, like we do, 500 records, that's of course different than if you have a product database like bol.com with millions of products. So it's really hard to tell. Yeah, it's really experimenting. That's the only way to find out. Sorry, I would love to give you like an answer like per record 1,000 or something, but it's not there. No.
Well, one of the good things is that we did see that with a small judgment list, we could improve the search for rolling pretty well, actually. So, it really depends.
Which was a bit cheating.
Yeah, a little bit.
Come to our booth if you want to know the cheat. We didn't cheat with the model, by the way. That was all real, but it's it has something to do with how we created the judgment list. So if you want to get the ins and outs in that case, then come look us up. There's this nice feature in the app where you can track speakers, so you know where we are, and you should be able to find us. Other questions? I think it's time for lunch. Yeah, thank you.